In this session, we're going to see how to use a tool called Descartes' rule of signs. And it's just what I said, a tool. A tool for your toolbox that, together with a bunch of other tools, can help you to find zeros of polynomials. And polynomials, as you know, have degrees. So let's suppose that we have a polynomial p and it's a fifth degree polynomial. It turns out that a fifth degree polynomial has at most 5 zeros. Zeros are also called roots, and they are all solutions to an equation, polynomial set equal to 0. And those 5 zeros can either be real or complex. Here's the deal with complex zeros. Complex zeros always come in conjugate pairs. And to convince you of that, let's consider the quadratic formula, which will give us complex solutions if the discriminant is negative, and since there's a plus or minus before the radical, that's the conjugate pairs business. So if we have at most 5 zeros for a fifth degree polynomial, then it could be the case that all 5 of them are real and none of them are complex. Or it could be that 3 of them are real, because if I have one complex, I'm going to have 2, right? Conjugate pairs. Or one of them is real and the other 4 are complex. These are all the possibilities. For these real ones, they could either be positive or negative. Descartes' rule of signs is a way to indicate how many of them might be positive and how many of them might be negative. Here's the kicker. It doesn't tell me anything about the complex zeros. This just gives us possibilities. Let's see how it works. We're asked to use Descartes' rule of signs to determine the possible numbers of positive and negative real zeros and complex zeros. Here's how Descartes' rule of signs works. Look at the sign of each term of the original polynomial. In this case, f of x is equal to 2x to the fifth plus 7x to the fourth minus 4x cubed plus 8x minus 9. 2x to the fifth is a positive term, so is plus 7x to the fourth. Minus 4x cubed is a negative term, plus 8x is a positive term, minus 9 is a negative term. Descartes' rule of signs asks us to look at how many times terms go from positive to negative. The first two terms, 2x to the fifth plus 7x to the fourth, both positive, we don't care then. But from 7x to the fourth to negative 4x cubed, that's a sign change. From negative 4x cubed to 8x, that's another sign change. From 8x to negative 9, another sign change. So here I have 3 sign changes. That means I could be expecting 3 positive real zeros. That discussion about complex zeros, though, indicates that we could be looking at possibly 3 or 1 positive real zero. Okay? Remember, if a zero isn't real, it's complex, and those things come in pairs. So 3 or 1 positive real zeros. What about negative real zeros? For that, we consider f of negative x. Now let's brush up on our algebra just a touch. Suppose I have negative x squared. We know that means that we have negative x times itself, and negative x times negative x is going to be positive x squared. Keep that in mind for a moment, and let's consider now negative x cubed. Negative x cubed means to multiply negative x by itself 3 times, and since there is an odd number of negative factors, the answer is going to be negative x cubed. We're going to use that information. Here we've got 2x to the fifth plus 7x to the fourth minus 4x cubed plus 8x x minus 9. And since we're evaluating at negative x, I'm going to put a negative x everywhere we see an x. Now we go back to what we just saw. Look, if the exponent is even, that means I have an even number of factors, and there's no change, right? It eats negatives, essentially. If the exponent is odd, then I have an odd number of factors, and that induces a sign change. So when we evaluate the polynomial at negative x, that first term, when negative x is being taken to the fifth power, we're going to end up with a negative for that term, negative 2x to the fifth. For the next term, negative x to the fourth power, that even exponent essentially eats negatives, and so that doesn't change, plus 7x to the fourth. The next term has an odd exponent, so negative x to an odd exponent, that's going to make the term change signs. So we end up with positive 4x cubed, and then again for 8 times negative x, that's going to give me a negative 8x, and then minus 9 doesn't have a variable, so it's unaffected. Now we're going to look at sign changes, but not how many terms change signs from f to negative x. That's not what we're after. We're after, look, the first term is negative. The second term is positive. That's a sign change right there. Third term is positive. Fourth term is negative. That's another sign change. Fifth term is negative. So anytime terms in order go from positive to negative or negative to positive, that's a sign change. So here we have two sign changes, which means we can expect two negative real zeros. Let me scroll up a bit. In other words, positive and negative values of terms in f of x tell me about positive real zeros. Considering f of negative x tells me about negative real zeros. Let's look at this as a chart. So we could have real zeros, we could have complex zeros, and the real zeros could either be positive or negative. This chart, essentially we're going to use it to examine all the possibilities we have. Scrolling up a bit, I see that we were expecting up to 3 positive real zeros. We're also expecting up to 2 negative real zeros. If we have 3 and 2, that's 5. This was a, let's scroll up, 5th degree polynomial, and so I'm expecting at most 5 zeros. So if I have 3 positive and 2 negative, there are none that could be complex. However, remember up here we explored the possibility that if we have a complex zero, we'd have 2 of them, and so I may not have 3 positive zeros, I may have only 1 positive real zero. If we have 1 positive and 2 negative, then we would have 2 complex zeros. And look at this, the total number of zeros is 5, whether we have 3 positive, 2 negative, and no complex, or 1 positive, 2 negative, and 2 complex is still a total of 5 zeros. There's something you may be noticing that we kind of left out just a little bit, and that was, wait a minute, we talked about OR for positive real zeros. What about OR for negative real zeros? Well, if I had 2 negative real zeros possible, and one of them goes complex, then 2 of them are going to go complex. So it could be the case that I have no negative real zeros. Let's revisit this chart. So another possible combination would be I have 3 positive real zeros. I have no negative real zeros because 2 of them were complex. Again, the total for each row is 5. Finally, what if I have 1 real zero that's positive, no negative real zeros, Well, let's see. 1 positive means that 2 are complex. No negatives would mean that 2 more are complex. That's a total of 4 complex zeros. And again, we have a total of 5 zeros possible. Let's cut to the chase here. F of x sign changes told me that I was expecting 3 or 1 positive real zero. F of negative x, those sign changes, indicated that I was expecting 2 or 0 negative real zeros. Our process for finding zeros is going to be to make a list. Positive and negative in front of the elements in the list, and the list is obtained using the rational zeros theorem. If you're not sure about that, there's a video. From this list, I'm going to guess. After I've made a guess, I'm going to use synthetic division to find factors. Factors tell me about zeros. That's the factor and remainder theorem. If I can see that I'm expecting 2 or 0 negative real zeros, that means I'm not guaranteed one. If I'm expecting 3 or 1 positive real zeros, that means I am guaranteed a positive real zero. So my guesses, I would probably start guessing with a positive number. I'll be the first to admit this is kind of a weird thing to say. Look, we go through a process and we find out maybes, but it's one tool in your toolbox. Use it as you want to.